Come on, there we go. All right, I'll begin with a word of prayer. Dearly Father, we thank you for this day. Again, I thank you for these students. Just ask you to bless our work today, help us to glorify you what we do. And we just thank you for your many blessings, Lord. In your name I pray, Lord Jesus. Amen. All right, so here's the attendance sheet, lest I forget. Of course, the Top Hat code's over there if you like that sort of thing. Let me just dive straight into it. I have some examples. Now, you know, we're going to cover some applications of first-order differential equations today. We've already covered some, right? I talked to you guys about how to find orthogonal trajectories, talked about how to find integral curves, right? Those are applications right there. We talked about how to, construct a differential equation which has solutions that are like increasing one place and decreasing another. Remember we looked at that? So all these things are applications. But I'll just dive straight into it. Let's do a new one. So example 1. Suppose we have y squared equals to kx, right? Find the orthogonal trajectories to this. So there's a few problems like this, I think, in your homework. And so the immediate question is like, how do you figure out what dy dx is, right? Because to find the orthogonal trajectories, we need to find, dy, basically, just, here's the roadmap. What we're trying to do is dy dx for the, for the orthogonal trajectories is going to be equal to minus 1 over dy dx for the given, for the given curve. But, so first of all, first order of business is to find dy dx. And the question is, how do you do that in a situation like this? And so the answer, there are probably more than one answer, but one answer I like is solve for k. K is equal to like y squared over x, right? And once I do that, if I differentiate, the constant goes away. You see? So if I differentiate, this gives me 0 is equal to like 2y over x dy dx, minus y squared over x squared by the product rule, and also, of course, the chain rule. We're assuming y is a function of x. This is implicit differentiation, remember? Like Calc 1? Okay, so now we can solve this for dy dx is equal to what? We got ourselves a y squared over x squared times the reciprocal, which is x over 2y. What's this give us? We got here? We got y divided by 2x, it looks like, right? So this is the given family's derivative, right? So then to find the orthogonal trajectories, I want to solve a related but different problem, which is dy dx equals to minus 1 over y over 2x, right? But that is, minus 2x divided by y. And how do we solve that? I'm thinking separate and integrate, right? So I got myself y dy equals to, minus 2x dx. Integrate both sides. That gives us a 1/2 y squared is equal to minus x squared plus a constant. And there you go. That is the orthogonal, those right there, that's the orthogonal trajectories to the given curve. So, any questions? Yeah.
Did you put it in the explicit
form? Well, I didn't ask for that. And, I guess maybe an improvement might be this, right? This is the same as x squared plus y squared over 2 equal to a constant. So if I put it like that, that's kind of better, because then you can see that the solutions are what? It's an ellipse centered at the origin with like major axis 1 and minor axis, I guess 1 over root 2, like root 2, something like that. Wait a minute, root 2 is the major, 1 is the minor, I suppose. But, solving for y, well, I'd need more information here, right? So I wouldn't probably do that here. Other questions? Yeah.
In the first step, how'd you get from a equals y squared over x to the 0 equals?
Oh, so, you know, this is a product of functions, right? Y squared times 1 over x. So if I differentiate k, I have the derivative of y squared times 1 over x plus y squared times the derivative of 1 over x, right? Product rule. And the derivative of y squared is 2y dy dx. And the derivative of x, 1 over x, is minus 1 over x squared. So it's the product rule. Other questions? No? All right. All right, here's another example we can work. If I can find a marker that behaves. Actually, some of these markers are getting low already. So here is example 2. Find velocity of mass m, which is launched vertically with velocity v naught from a planet with mass m and radius r. So here's a little recollection. The force due to gravity, remember, is equal to minus big G, little m, big M, divided by the radius of the planet plus y, where y is the altitude, squared. So if we assume the motion is directly vertical and y is the altitude of m, the question is, find the velocity as a function of y. All right, so this is most certainly an applied problem, right? So brought to us from physics. Kind of tired of this marker. I'm going to stick it over here. All right, so Newton's second law says what? F equals to what? ma, right? Now we're assuming that the motion is vertical, which means that we don't need to think of it as a vector. We can think of it as a one-dimensional problem. So this in particular is m dv dt, which we can write as m dy dt times dv dy, since the motion's one-dimensional. In other words, we've got m v dv dy. We make this kind of sneaky chain rule step. This will allow me to find the velocity as a function of y directly with calculus. Now this is the force as it relates to the mass times acceleration, written in terms of velocity and the derivative of velocity with respect to position. I'm going to put that equal to minus big G m over r plus y quantity squared. Now here r is a constant, big M is a constant, little m is a constant, right? The only thing that's variable here is v and y. Can we solve this differential equation? I think so. This is considerably easier than a lot of the ones you're stuck on in the homework at the moment. So let's see here. What we got? We got ourselves a v dv is equal to, what we got here? Minus g, big M. The little m's, they decanceling, right? So minus big GM over r plus y quantity squared. There's a dy here, right? And I think if I read the problem statement more carefully, we're assuming that it's launched vertically from the surface of the planet. So like let's assume that the initial y is like this. When it has velocity v naught, we're going to assume y naught is equal to 0. All right. So the initial y is 0. All right. So then let's get to it. Integrate from v naught to vf. Integrate from y naught to yf. So they have to be matching bounds. That is the content of the change of variables theorem, basically. Now integrating v dv just gives us 1/2. We get ourselves a 1/2 vf squared minus v naught squared is equal to, let's see here, I think that just integrates to big GM over r plus y. And we have to evaluate that from y naught to yf. Right? If you differentiate that with respect to y, you get back minus GM over r plus y squared, right? So my antiderivative is legit. Some might say too legit, but I wouldn't say that, because that would tempt me to say something else. And then I wouldn't want to quit, but I won't say that. So v squared equals v naught squared plus, sorry, I'm an idiot, but you already knew that. So GM 1 over r plus y minus 1 over r, like that. So to go from that step to that step, I'm making yet another change in notation here. I'm putting yf equals to y and vf equals to v. All right. And so finally, I find the velocity as a function of y is apparently the square root of v naught squared plus gm 1 over r plus y minus 1 over r. Of course, you could simplify that and make a common denominator, but I'm just going to leave it like that. So there you go. That is the velocity as a function of y. Yeah.
We lose the 2 and the 1/2.
Yes, I think I do owe you a 2 somewhere, at least 2 of them. You could say I owe you a 2, but nobody wants that. So put a 2 here and put a 2 here. I think that's it, right? Okay. Thank you. I do appreciate it. Oh, hey, there's a 2 in my solution. I also have a plus minus in my solution, but I don't really believe that. Yeah, I mean, I guess I should have a plus or minus, and then fine. I'll put the plus or minus in. I guess the minus is there mathematically. I mean, physically speaking, because what goes up might come down.
But it can't go.
Well, it could go on forever, though. I think it kind of depends on what v naught is relative to. Yeah. I mean, that's a question. Is there any choice of y which makes this 0? Right? Does the velocity ever become 0 in the motion? So that we can't answer without more details. Like, it depends on how big v naught is relative to this term over here, you know? So I will do another example here. Let's see here. Let me do something that's a little bit different. And I'm sorry I didn't have one of these in the collected homework. I really should have. This is kind of a standard, like, applied problem. And for shame that I haven't made you, like, work one out and turn it in. That's my bad. Oh, man, I never moved the camera. I'm an idiot. So the next problem is about a mixing tank. You have a tank initially contains 100 gallons of water with 10 pounds of lemon drink mix. Then at t equals to 0, fresh water is added to the tank at 3 gallons per minute. All right, 3 gallons per minute. And at the same time, 3 gallons are drained per minute from the tank. Assume the tank is well mixed during the process. Find the pounds of lemon drink mix as a function of time. If you like your drink with a concentration of 1 pound per 20 gallons, at what time should you drink from the drain? Okay, so example 3. All right, so we've got, I'll draw a picture here. So this is a 100-gallon 100-gallon tank, all right? And we have, let's say Y equals, pounds of lemonade mix, all right? And so we're given that we have the initial amount of Y is 10, all right, 10 pounds. And then we're told at t equals to 0, fresh water is added to the tank at 3 gallons per minute. And at the same time, the tank drains 3 gallons per minute. All right. Let me add to my picture a little bit. So I'm saying that we've got, some kind of fresh water. And it's coming in, what did I say, 3 gallons per minute? And when I said what else, there's a drain down here, right? And it's also exiting 3 gallons per minute. And what else? What's the other stipulation here? The tank is what? It's well mixed, right? So you can imagine there's like a big paddle in there and it's mixing it. So the assumption then is that the lemonade mix is uniformly mixed throughout the, throughout the tank as we go on. Okay? So, well mixed. So what we want to do is write down a differential equation which describes this. And so this is part of like a general family of examples. They're all kind of the same principle. And the principle is this, is that we want to write down a differential equation, dy dt is equal to the rate out, right? Rate in rather, rate in minus the rate out, right? So the rate in is, let's see here. The rate in, so what are we talking about? Are we talking about rate of water? What's Y?
Lemonade.
Lemonade, right? So are we adding any lemonade to the tank? No, we're not. So the rate in is 0, right? You can imagine another system where you're adding, a continuous sprinkle of like 1 pound per minute or something, right? That would be a different problem. That would put something here. But that's not here. So what we do have is 3 gallons per minute going out, right? So let's think about that. So to get the rate out, how do we do that? We need to think about things here. So this should be in what? Let's think about the units. We're looking for the rate out in pounds per minute. We're gonna work in minutes, all right? Pounds per minute. We're gonna let t be in minutes because that's what's given to us, that's what's natural. So how do I figure out the rate out in pounds per minute? Well, I have to take my 3 gallons per minute, right? And I have to multiply it by something logically to get what? The pounds per minute. So what do I want to put there? So what does the rate of lemonade per gallon depend on at any particular time? It depends on how much Y is in the tank, right? So this should be a function of Y. So what we want here is Y, but the units wouldn't be right on this yet, right? Because Y is in pounds. So this would give me a pounds gallon per minute. So what we have to do is actually multiply by the so-called concentration. So I take Y and I divide by 100 gallons. Now if you look at it, dimensional analysis says that we're on the hunt because the gallons, they'd be canceling, and we've got like pounds per minute if you look at this expression, right? So to come back over here, we simply have minus 3Y over 100 because I'm not going to write units because I'm not a punk. So, although you might disagree, free to disagree, dy dt, I do grade your stuff though, dy dt, but you might say, well, you're not a petty man, so you won't take off points just because you call me a punk. And that's probably true, right? But what if I am petty, actually? I guess you'll find out. Let's see here. Dy over y is equal to like minus 3 dt. So we separate, we separate integrate, right? Let's integrate from y0 to yf. Correspondingly integrate from time 0 to time tf. That gives me, natural log the absolute value of yf minus natural log the absolute value of y0 equals to minus 3tf. I will continue this exciting solution on the other side of the board. If we solve for y, we get what? Y of t is equal to y0 e to the minus 3t after a little bit of algebra. But we know what y0 is, right? Y0 is what? It's 10, right? So I have 10 here. 10 e to the minus 3t. That's the amount of the pounds of lemonade mix. Yeah. Say again? Oh, did I lose my 100? Oh no, that's no good. Thank you. Yeah, that's gonna make a difference. Yeah, I do appreciate corrections in the middle. Like in Math 200, I managed to complete the square wrong this morning, and my evil son is sitting there. He sees it from the start. He says nothing. Then a decent human being, another student in the class, is like, "Hey, doesn't..." And so this is how sad it is, right? Like the thing I'm factoring this morning was this. No, 3. And so I had completed the square because I love completing the square, and I wanted to show them how exciting completing the square is. But one of them pointed out to me that I could have done this, which was not intended. That was an accident that happened, which I did not see. And so it is part of your exam, though, probably. Maybe not that exactly, but roughly speaking. Okay, so this is the pounds of... Now that doesn't answer the question, because what was the question? The question was, at what time should you drink from the drain, right? If you like your Kool-Aid to be mixed at what concentration did I say? I said you want to drink Kool-Aid when you got 1 pound per 20 gallons. You prefer 1 pound per 20 gallons because that's just the kind of thing you know. Right? 1 pound per 20 gallons. What time should you drink? So what would that mean then? Let's think about this. So y that you're interested in, y drinky drink, y drink should be what? How many? If it's 100 gallons, right? Because the volume stays constant at 100, right? So if I want 1 pound per 20 gallons, I need what? How many pounds altogether here? 5 pounds. Very good. If I have 5 pounds overall, that means I have a concentration of 1 pound per 20 gallons. So I need 5 pounds. So the time I'm interested in drinking is when this is equal to 5. So 5 is equal to 10 e to the minus 3t over 100, which tells me that 1/2 is equal to e to the minus 3t over 100, which tells me that the natural log of 1/2 is equal to minus 3t over 100, which tells me that the time for drinking is 100 times the natural log of 1/2 divided by minus 3. That's when I would like to drink the Kool-Aid. Excuse me, lemonade. No Kool-Aid drinking. Man. I was hoping I had a decimal here, but I don't. So we'll just have to deal with this. If you don't like the minus, you could trade this for this. This is 100 times the natural log of 2 divided by 3. So whatever, that's the time that you should drink, though. Okay? So that's a pretty standard applied problem in this kind of course, right? And you can add all kinds of bells and whistles. You can make the volume of the mixing tank vary, right? That makes the concentration formula ever so much more interesting because then your volume is a function of time, which then makes the concentration a more complicated function of time. There's all kinds of modifications we could make of this thing, all right? So any questions before I go on here? Oh, I asked you guys.
Well, like intuitively, like, what were you looking at?
Well, you want, I mean, I guess it's a ratio if you want me to make some work for it instead of just figuring.
Is it a proportion?
It is a proportion. So we want 1 pound per 20 gallons
Is equal to 100 gallons per X.
is equal to, yeah, we don't know, y over 100.
Okay.
So apparently y should be 5. Yeah.
How did you go from the, where you were running right next to each other, right, the ln of yf minus ln, how did you go from that to the y of t is equal to 10t to the negative 3t over 100?
How'd I go from here to here?
Yeah, so
Cause-
on the right side of the board
This?
above that.
That?
To the y to t.
Algebra. So exponentiate this equation. We've done this before. So if we exponentiate, so I've got natural log of y minus the natural log of y naught equals minus 3t over 100. We exponentiate both sides. First of all, that's the natural log of y over y naught.
Yep.
And I don't need absolute values here because it's clear that the y and y naught are positive. I exponentiate both sides. This gives me y divided by y naught is equal to the exponential of minus 3t over 100, which then gives me y is equal to y naught e to the minus 3t over 100. So that's the algebra I had deprived you guys of. But basically, you just exponentiate the equation and solve for y. Good question. Good question. I want to ask a more difficult physical question here next. This one actually is going to be really a lot more novel, perhaps, for us. So that question I have is basically, I think this is a problem we probably haven't solved before. I don't think you would have seen this in your physics class, and the reason for that is that you actually needed, differential equations to actually solve this problem. But I think it's an interesting problem. And so the problem goes like this. Suppose you've got a chain, all right, and it's a very, say, fine, it's got very fine links. So essentially it's got a uniform mass density, all right? You got a chain, it's lying in a heap on the ground. And one end is lifted with constant force, all right? The question then is to find the velocity, all right? So where am I? This is example 4. I'll draw a picture. So we've got, a coiled chain here, right? And then you're lifting it with a constant force F naught, right? Lifting with constant force. Supposed to find the velocity if you lift it with constant force. Now we're assuming that this chain is close to the surface of the Earth, right? With Earth's gravity. And also, I'm going to set some terms for us. We're going to call the length of the chain which has been so far lifted x. All right, so this is going to be x. We're also going to assume that the mass, that the dm dx is equal to lambda. This is constant. There's a constant mass density. So, in other words, I could just say that the mass of the chain that's been lifted at a current point in time is equal to lambda x, right? There's some constant times x, which gives me the mass which has been lifted. Are we good? That make sense? So, what's the velocity then in view of that? So we're trying to find what? Our mission, should we choose to accept it, is what? We're trying to find dx dt, right? That would be the velocity that we're interested in. How do we do that? So what is Newton's second law? What does it say? F equals ma would be incorrect. In this context, why? Why is F equal ma not the correct Newton's law here? No, I didn't say that. There is acceleration. Mass is not constant, right? F equals ma is only for constant mass problems. More generally speaking, Newton's second law says that dp dt, right, and dp dt is equal to the net force. But that's the momentum, right? Momentum is mass times velocity. So, and the net force here, let me get that out of my system. What is the net force? There are two forces, right? Yeah, F naught, which is apparently just a constant force, that's given, right? You're just pulling up on it with constant force. Yeah, you're getting into the, but minus the weight, right? Minus mg, which you're right, that would be lambda xg if we were more, you know, it is true, you could write that as equal to F naught minus lambda xg, that is true. There we go. Okay, so let's get into it then. So I have that dp dt, let's work on that. What is that? That's equal to ddt of mv, right? Which, by the way, is dm dt times v plus m dv dt. So there's your ma term, but there's also this new pesky dm dt times v term, right? So that's kind of new. Okay, so then what? Well, this is all equal to, can we simplify this? What are we looking at here? What is dm dt? So we have ddt. What is m? M is lambda x. So that times v plus, m times dv dt. Let's see here. Oh, but the dv dt, we could trade for, remember that thing we just did in the other example? We traded it for v dv dy. Let's do that again here. Let's trade dv dt for v dv dx using that trick. Since it's one-dimensional, we can get away with that. I think that's what I want to do. Let me check my solution for a second. Because I'm trying to find the velocity. Yeah, that's what I did. Okay, cool. All right, so what is this? This is, lambda's a constant, right? So I've got dx dt times v plus m, well, m was what? Let me put all my lambdas in. That's lambda x, v dv dx. That's all equal to what? This, of course, is dp dt, but that's equal to f naught minus lambda xg, right? Let's see here. But what's dx dt? This is v again, right? Dx dt is v. So what do we got? What are we up against here? Looks like we're up against lambda v squared plus, lambda xv dv dx f naught minus lambda xg. So this is definitely not a differential equation I would try to solve mid-physics 231. In 231, I'll do separation of variables. Everyone can learn separation of variables. It's not a big deal. But this is something else. Yeah.
Could G be written in terms of velocity? Is that possible? Or
Could what?
could G be written in terms of velocity so that you can cancel? Oh wait, actually, you can't cancel.
Well, G is a constant. It's 9.8. Yeah. Let's see here. All right. So, man. Uh-oh. So let's divide by lambda and see what that gets us. So we get v squared plus xv dv dx equals to f naught over lambda minus gx, or minus xg if you like. And so what I do at this point is I make a w equals v squared substitution. Now why did I do that? Yeah, if I do this, that makes what? That makes dw dx equal to what? 2v dv dx, right? So in view of that substitution, marker's trash. Let's see here. If I can find a better marker. Oh man, I think I'm out of good black markers at this point. Oh well. All right, so we get v squared, which is w, plus, now notice that v, we got the x there, right? So 1/2 dw dx. That's my left-hand side. That equals f naught over lambda minus gx. If I haven't made a mistake. Can we clean that up? Can you solve this differential equation? I think we can. Let's see here. We have dw dx plus 2 over x times w is equal to 2 over x times f naught over lambda minus gx. So what I did was I rewrote these in the opposite order, and I multiplied the whole equation by 2 over x. That cancels out the x over 2, right? And it also reveals that, hey, this is actually, what? What we got here? We have 2 f naught over lambda x minus what? Just 2g, right? What's this? Yeah, this is a linear equation, so we can solve this. So notice, x squared is the integrating factor. So if we do x squared times dw dx plus 2xw is equal to, well, multiply by x squared here. So 2f naught x over lambda minus 2gx squared. So the integrating factor method, you have to integrate 2 over x. But the integral of 2 over x gives me a twice natural log of the absolute value of x inside an exponential, which, is x squared. So that's why I multiplied by x squared. And the proof's in the pudding, right? I mean, it worked. So this is d dx of x squared times w. So you can see that I was right in my calculation of the integrating factor. Because if I hadn't been right, this reverse product rule wouldn't have worked for us. Now, integrate both sides. We get x squared times w is equal to f naught x squared over lambda minus 2/3 g x cubed plus a constant, I suppose. Let's see here. What was my w? W was what? W was v squared. So if you allow me this short manga style calculation in the red, This is v squared x squared, or x squared v squared if you like that, if you prefer that way of writing it. And then, of course, I can solve for v squared equal to, apparently, f naught over lambda, the x squared, it'd be canceling, and minus 2/3 gx plus c over x squared. Let's see here. Now what should, oh, it's funny that this formula breaks down when we first start pulling the chain, right? And if you think about that for a second, it kind of makes sense, because if you pull the when you start pulling the chain with a constant force F naught, your constant force of F naught is applied to an infinitesimal amount of chain being lifted. How's that work? Well, that gives you an infinite impulse, because the mass is infinitesimal at that initial moment of pulling. So like, it's not physically possible to pull with constant force over the whole duration. So I'm just going to, stick a fork in it. It's done here. So V is the square root of like F naught over lambda minus 2/3 gx plus some constant divided by x squared. But probably the way to make this problem physically reasonable is I can't start it. I have to lift some amount of the chain and then start pulling with a constant force after that point to make it a physically reasonable problem. Right? If we try to extrapolate back to x equal to 0, it doesn't make sense physically speaking. So, any questions? Yep.
How do you know set W over V squared?
Oh. Well, I did it when I solved this problem before. Is the major reason. But let me see if I can find you a better reason. I suspect this is a Bernoulli equation. Let's see here. This, if we look at, right, let's trade this. This is dv dx. How's this go? dv dx plus, if I divide this by xv, I've got like 1 over x times v equals to f naught over lambda minus gx, right? And I'm dividing by xv, so I have a v to the minus 1, let's say, over x, right? So if you do that, you can see that the equation that we were facing at the start is in fact a Bernoulli, right? It's Bernoulli with n equals to minus 1. And what was the rule? What was the rule for the Bernoulli substitution? Do you guys remember? What was that rule for the Bernoulli? Yeah, w equals y to the 1 minus n. Is that what I did? Well, v is the y here, right? So w equals v to the, is this n equals minus 1, 1 minus n? 1 minus a minus 1 is v squared. Woohoo! Yeah, that's why we did it. It's Bernoulli. So, but it's been a minute since I wrote a solution. But yeah, it's Bernoulli. It's the Bernoulli substitution. Yeah. So, yeah, Bernoulli equations actually come up in real physical problems, like this. Yeah.
On the first board, when you go from blue to red, how does that first term become lambda v squared?
Oh, that's because the x dt is v.
Okay.
Uh-huh.
Change of position and change of
Other questions? All right, let me get the projector out here. I think there's a problem in the notes I'd like to show you guys, but I don't. Was there a question? No question.
Is it necessary to, when you're doing the W substitution, is it necessary to have it over dx on both sides? dw dx?
My substitution was w equals v squared. This is just differentiating. So So like dw dx is the chain rule, 2v, the inside function being v, so 2v times dv dx. This is like just differentiating that equation implicitly.
We're differentiating it with respect to x.
Yeah, yeah, because both w and v are functions of x in this scenario.
And x
Now-
would be considered position.
Yeah, x is the length of the chain that's been lifted. Yes, sir.
How did x equals 1/2 dw dx become 2 over x w at the top?
That is an algebra step. I multiply by 2 over x. So when I multiply by 2 over x, cancels this one, leaves me w dx, right? This piece becomes that piece, and this piece becomes that piece. When I multiply by 2 over x, I get 2 over x times w. Yeah. It's always algebra.
Yeah, I thought you differentiated first. I was like, how do you
Yeah.
do w?
It's either algebra or calculus. I mean, it's one of the two. So, but these are good questions. It's fine. Ask away. So, let's see, what was I going to tell you guys? Oh, yes. I was going to give you guys a bit of a hint on how to attack that isogonal problem, because there's a problem in homework about showing that a particular formula has to hold for an isogonal trajectory. All right. So if you really look at the problem, what it requires you to do is to figure out how do you rotate a vector in the plane. So that's a question. Like, what's the mathematics? What's a good way to mathematically rotate a vector in the plane? And I suppose there are many answers to that, but one answer which I'm kind of fond of is to use complex notation. All right. So let me show you some basic examples of this. If I have the vector a comma b, right? In complex notation, this becomes a plus bi. So in the complex plane, two-dimensional vectors are implemented as complex numbers. Every complex number is a two-dimensional vector. If I take this two-dimensional vector and I multiply it by I, what do I get? I get IA plus b times I squared. Now I squared is minus 1 because that's what I is. I is the square root of minus 1. Its square is minus 1. So this gives me minus b plus IA. All right? Where is that graphically? So that is over here. This is the vector minus b comma a. What have I done? I have rotated 90 degrees. So multiplication by I rotates a vector in the counterclockwise fashion 90 degrees. Okay? This is a plus IB rotated counterclockwise 90 degrees. Now, I'll just get straight to the point here, guys. Any complex vector, any complex number, which is a two-dimensional vector, can be written as a magnitude times a direction. So we can write this as, r cosine theta, r sine theta, but we can just as well express that as r e to the I theta, where e to the I theta is cosine theta plus I sine theta. All right? So any point in the plane has a polar coordinate representation, and in the complex notation, it just looks like r e to the I theta. All right? Now, it turns out that this is the so-called imaginary exponential, and it has wonderful properties. Chief among them being this: e to the I theta times e to the I beta is equal to e to the I theta plus beta. I'm not going to prove that in here, but you can check. That single complex equation right there folds into it implicit within that equation is both the adding angles formula for sine and the adding angles formula for cosine. Namely that sine of theta plus beta is sine theta cosine beta plus sine beta cosine theta. I switched the order of theta and beta in the sine and cosine there. And also that cosine of theta plus beta is cosine theta cosine beta minus sine theta sine beta. These are the adding angles formulas for sine and cosine. Both of those identities are wrapped into that single imaginary exponential formula. So here's the deal. If I take z is equal to r e to the I theta, and I multiply it by e to the I beta, what happens? I get r e to the I theta, e to the I beta, which gives me r e to the I theta plus beta. What this is z rotated by beta. So if you want to take a vector and rotate it by plus or minus alpha degrees, what you should do, you want to take a vector v and rotate by plus or minus alpha. I should say radians. This is all radians, of course, but except 90 degrees up here because that's my happy place. Sorry. Pi over 2. Does that make it better? Not really. But then at least these formulas would be valid. So plus or minus alpha radians, what you do is you just take the vector v written as a complex number and multiply it by e to the I, well, plus or minus I alpha, right? So logically speaking, this isogonal trajectory problem in your homework, you can use this as a hint. See, if you can take your initial family of curves, which you can parameterize by x as follows, right? If my initial family of curves is parameterized by r of x, so it's got like x comma y, then if this is the parameterization of the initial family, what's dr dx? It's what? It's 1 dy dx, right? Which is to say 1 comma f of xy in the problem that I'm talking about. So you see the initial velocity for the given velocity, right? The given tangent vector direction, right? The given tangent vector direction, you could write in the complex notation as what? 1 plus I times f, right? So that's the given direction vector to the family of curves in that problem, right? If you're solving dy dx equals to f of x comma y, if you write a solution parametrically in terms of x, so this is like, solution parameterized by x, then that would be the parameterization of it, right? If I differentiate the parameterization with respect to the parameter, that gives me what? That gives me the tangent vector, right? The tangent vector to the curve, which is 1 comma dy dx. But dy dx is given to be f of x comma y in that problem. So great, this is the direction of the tangent vector to your initial curve, right? So this is the given curve. So this would be the given. You're trying to, in that problem, come up with the differential equation that's needed if you have your intersecting curve like this, right? At alpha degrees. But the thing is, you don't know if it's alpha degrees clockwise or alpha degrees counterclockwise. So technically speaking, you have to multiply by plus or minus the rotation by alpha. But both of these can be achieved if you use my hint, which is to take the velocity which is given and simply multiply by e to the I plus or minus alpha. But again, this is a specific complex number. You can work it out. And when you do that, you'll be able to derive the formula which I asked you to derive. I know because I did it. I tried to do this without imaginary exponentials, just with like dot products and like typical Calc 3 geometry. And I've got a page and a half, and I just didn't get it. Now maybe you'll get it a different way. You don't have to use my hint if you don't want to, but here's a path that you could try for that problem. But hey, it's just 1 point out of 50, so like, If you don't do it, it's not the end of the world. But I thought I'd give you a little hint here. Also, if you don't know about imaginary exponentials, there's no time like now to learn, because we will use them in our solution sets coming up very soon. So that said, let me get the projector out here. Any other questions about anything, guys? Uh-oh. All right, see if I can get this working. Do 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 do. Oh man, come on. All right. Let's see here. So you guys are working on mission 1, I'm guessing. Is there anything in here? I've got a couple minutes I can spend on questions you might have about the mission. I'm not going to work anything out, but I can give you advice, perhaps, if there's a particular problem you have a particular question about. This will be the last. I won't have time for questions about the mission next class, so this is it. Of course, you can ask questions in office hours if you have them. Anybody? Yeah, go for it.
It was the second problem on Claira's equation.
What about it?
I was stuck on it. I couldn't quite figure it out.
You mean the singular?
Yeah.
I mean, there's not much to say there except that I think the f of y prime is, f of, basically the f is the square function, right? Oh, no, my bad. That was what I was thinking before, but after I looked at it more, I was talking to one of you guys, we need to look at that problem. Which was that, 9? So I got, all right, so yeah. So mostly you just have to, use the, so if we look at this one, we have y is equal to x plus 4 times y prime plus y prime squared, right? That's given. So if we look at, reformat this is x times y prime plus parentheses 4y prime plus y prime quantity squared, right? So this whole animal right here is what we think of as f of y prime. So if I had to write that instead as a function of x, say, we're looking at 4x plus x squared. So pretty much you just go from there, use that and then you follow the instructions in the problem statement to construct the solution like we did in class. That's basically it. Other questions? Did you get, you had talked to me before about the